Section 7.3 is about integrals using trig substitution. What that means is we're going to take an integral that involves usually a square root of a quadratic, so a square root of something with x squared. And we're going to turn that into an integral that involves trig functions, which we can then do using last section stuff. And we do this by making what I call a reverse substitution. I don't think that's a commonly used term. But the idea is instead of letting a new variable u equal some stuff involving the original variable x, we will let the original variable equal some trig function of a new variable. We will need to use some trig identities. The ones we'll use will all be based on the Pythagorean identities, sine squared plus cosine squared equals 1. And they'll be in this video. They are also in the book, so feel free to look those up. You should memorize the ones that come up in this, or always have them with you when you are doing these types of problems, including on the test. Okay, so let's look at an example before we get the general strategy. So let's say I have this integral in front of me. I might at first try a u substitution. It looks like a u substitution might work. So maybe I'll let u equal x squared. Let's see what happens. If u equals x squared, du is 2x times dx. And then the integral turns into, well, up top I have the square root of 4 minus u. On the bottom I have u, and then I have the dx becomes du over 2x. Now, no matter how hard I try, I'm not going to be able to deal well with that 2x. I could realize that x is the square root of u and do some stuff, but it doesn't turn it into anything that I can do easily. So that's probably not the best way to do this integral. Maybe a different u, 4 minus x squared instead of just x squared. Well, the same sort of thing happens. I have this x that I can't really get rid of well. In fact, there's not really a good u substitution. Now, there are ways to do this integral using u substitution, but they're not pleasant. And you might try integration by parts or something, but it doesn't really work either. So instead, we're going to do this new thing, trig substitution. So we will let the old variable x equal 2 times sine of a new variable that I'm introducing, theta. You could use u for this, but because it's playing the role of an angle here, I'm going to use theta. Well, if we make that substitution, we have to take the derivative to figure out the dx stuff. So dx will equal 2 times cosine theta times d theta. And let's also figure out what all the other things in that integral will be. X squared, well, that's just the x thing squared. So 2 sine theta whole thing squared, which is 4 sine squared theta. And then this square root thing on top. So the square root of 4 minus x squared is the square root of 4 minus 4 sine squared theta. I can factor a 4 out there and then pull it out of the square root. So I have to deal with the square root of 1 minus sine squared theta. Now that does not look friendly at all. However, remember this trig identity, sine squared plus cosine squared equals 1. If I move the sine squared over, and then I think I changed which side things were on, I have cosine squared is 1 minus sine squared. So that means that 1 minus sine squared under the square root I can replace with just plain old cosine squared of theta. And the square root of cosine squared is just cosine. Well, almost. Technically, the square root of something squared is the absolute value of that thing, but there are a few technical details that I'm sort of not telling you about in this video that you don't ever actually have to think about, but they had to be worked out to make sure this method will theoretically work. You can read about them in the book. What it really comes down to is we specify a particular domain for theta in this, and then everything works out. So we don't have to worry about those absolute values, and that's the case for all the trig substitutions. You don't have to worry about absolute values. If you have the square root of something squared as a trig function, you can just make it the something without absolute values. Okay, so let's see what happens to the integral now that we've worked all that stuff out. The integral will turn into, well, I have the numerator, the 4 minus x squared under a square root. I just figured out that's just 2 times the cosine of theta. The denominator, x squared, is 4 times sine squared theta. and the dx is 2 times cosine theta d theta. So I have a 4 in the numerator and a 4 in the denominator. They cancel, and I just have cosine squared over sine squared, also known as cotangent squared. And then you can finish that using the techniques from section 7.2. It's not too hard, just use another trig identity and then you're good to go. But the idea is we take that square root of a quadratic integral and turn it into an integral of a trig function. So that's trig substitution. So let's think about what substitutions work in general. And these work because of the way the trig identities work out. So if your integral involves the square root of a number squared minus variable stuff squared, so a is a number, the stuff involves the variable, you want to make the substitution that stuff equals the number times sine theta. So in the previous example we had the square root of 4 minus x squared, so the stuff was just x, so x equaled, well, 4 is 2 squared, so x equaled 2 sine theta. Okay, what if instead of number squared minus stuff squared, it's stuff squared minus number squared under the square root? Well, slightly different substitution. The variable stuff now needs to equal a times secant theta. And if the stuff squared and the number squared are added, you make the substitution of the stuff equals the number times tangent theta. Right, in all these cases, remember that a that I'm writing down is some number, some constant. And here I'm filling in which trig identities will come up as you're figuring out what that square root equals to put things in your integral. So in the top case, you'll use what we used in the example, 1 minus sine squared is equal to cosine squared. In the secant substitution, you'll use secant squared minus 1 equals tangent squared. And in the tangent substitution, you'll use 1 plus tangent squared equals secant squared. So we're going to do another example and see how some of this stuff works out. This one I'll go ahead and finish all the way through doing the trig integral. So let's say we're doing this integral and we see that nonsense. Well, what we've got is the square root of stuff squared, variable stuff squared, minus a number squared. That's 3 squared. If it weren't a perfect square, if that was minus 5 instead of minus 9, I could still use this. It would just be the square root of 5 squared, so a would be the square root of 5. But in this case, it's 3 squared, so a is going to be 3. So that means, according to the previous slide, the stuff should equal the number, 3, times the secant of theta. So x plus 2 equals 3 secant theta. And that means dx, if you take the derivative of x plus 2, you just get 1 dx, equals the derivative of 3 secant theta is 3 secant theta tangent theta, and then we have times d theta. So that's what I'm going to fill in for my dx. Now, what am I going to fill in for this horrible square root? Well, replace x plus 2 with 3 secant theta, and when I square it, I have 9 secant squared theta. So this is the first step in figuring out what that square root equals. I have the square root of 9 secant squared theta minus 9. Factor the 9 out and pull it out of the square root, it becomes a 3, and I have the square root of secant squared minus 1. Well, that trig identity tells me that secant squared minus 1 is tangent squared, and so the square root of tangent squared turns into just tangent, 3 tangent of theta. Now I can do the integral. So the integral, replacing everything with its theta version, is, well, this. Okay, so where did all that come from? The 3 secant theta tangent theta d theta is just dx, right? That's over here. The 3 tangent theta is what that square root equaled, and we worked that out right here. And the denominator, 3 secant theta, well, that's just x plus 2, right? Because originally we said x plus 2 was going to equal 3 times secant theta. Okay, well, we can do a little bit of algebra here. A 3 on top and a 3 on the bottom cancel, a secant on top and a secant on the bottom cancel, and so I have 3 tangent squared theta d theta. So now I have finished turning my original integral into a trig integral. That was the trig substitution part. Now we have to do this trig integral. Factor the 3 out and remember that tangent squared equals secant squared minus 1. I already used that identity once in here, but I can use it again. Because the reason I want to use it now, this won't happen in every trig integral, but the reason I want to do this now is that I don't know an antiderivative of tangent squared, but I do know an antiderivative of secant squared, right? The derivative of tangent is secant squared, so the integral of secant squared is tangent. The integral of 1 is just theta, if the variable is theta. The integral of 1 dx is x, and the integral of 1 d theta is theta. So I have 3 times tangent of theta minus theta plus a constant. Now I go back to x's. All right, back to my original variable. My integral started off being an integral in terms of x, so my answer needs to be in terms of x. So what's theta, right? Well, this requires a little bit more thought, but if x plus 2 equals 3 secant theta, I can divide through by 3 and then take the inverse secant, and I get that theta is the inverse secant, or the arc secant, of x plus 2 over 3. And I fill that in for both thetas. And that's one way to write the answer. However, it's a little bit nicer to use the triangle inverse trickery stuff on the tangent of the inverse secant, and we can rewrite that part of it with no trig functions. And you see that the strange square root of a quadratic that was in the original integral actually shows back up in the answer, and that often happens here. Okay. So, in case you missed it, how did I get that inverse secant of stuff? Right, so this was the substitution we had. X plus 2 equals 3 secant theta. That's the substitution I made at the beginning. If I divide through by 3, I get x plus 2 over 3 equals secant theta. And then I can take the inverse secant of both sides. On the right, the inverse secant of a secant cancels out, and I just have theta. And on the left, I have inverse secant of x plus 2 over 2. You could write that as arc secant instead. It doesn't matter. Then I also used some inverse trickery on the tangent of an inverse secant of something. Right? So I let the theta be the inverse secant of stuff and drew a triangle for theta. And then use that triangle to find the tangent of theta. Okay, so now you get to do a little bit. If I am asking you to do this integral, because I am such a mean person, what trig substitution would you use? I would like you to give me the equation that you'd use for the substitution. So in the previous problem, the equation was x plus 2 equals 3 secant of theta. What is it here? X stuff equals some trig stuff involving theta on the right. All right, so answer that question and we will talk about it in class. I will see you then.